I am modeling the outlet pipe of the heat exchanger, which has insulation surrounding it to prevent heat loss. And the insulation material that was chosen is rubber, since it's a relatively cheap material that works well as insulation. M- So this is my conduction equation for the analytical solution. I'm assuming fully developed and that the pipe walls are thin. Solving for this cylindrical conduction equation, it is at steady state, there is no generation, and it's 1D flow. To solve it, we integrate once to get C1 and we integrate again to get C2. There are two boundary conditions. The boundary conditions are convection at our inner and convection at our outer. In order to solve for these two, the temperature profiles in these conduction equations, we must plug in C1 over R for the river term and C1 natural log R plus C2 for the temperature profile. The two equations were subtracted from each other in order to obtain a value for C1 and in order to cancel out C2. After C1 was obtained, now we can plug it back into the equation to get a value for C2. After C1 and C2 are both known, we can plug that back into the temperature equation to solve for the temperature at our inner and the temperature at our outer. Next, finite differencing was used for the numerical approach. Both forward and backward differencing were used to find this. And the boundary conditions are the same, convection at our inner and convection at our outer. In order to solve for both the analytical and the numerical, H inner and H outer needed to be used. For H inner, T infinity I is equals to 50 degrees Celsius. That is the temperature of the fluid in the outlet pipe. The heat exchanger is heating the fluid. So the temperature of the water in the outlet pipe will be high. So 50 degrees is reasonable. The properties were obtained from the water tables, which is table A9. This was plugged into the Reynolds number, and the velocity was found from the flow rate and the continuity equation, which is also plugged into the Reynolds number. Reynolds number was found to be turbulent, so from the mass correlation table for internal flow for turbulent, we were able to get the Nusselt's number, which was then used to find H inner. As for H outer, we have T infinity naught, which is the temperature of the air outside of the outlet pipe, just temperature of the air. And the velocity, 6.7 meters per second, is the velocity of the air that is flowing around the pipe. Air properties from table A15 were used to obtain these values and were plugged into the Reynolds number in order to be used to find the Nusselt's number. Nusselt's number for cylinder, forced external convection from mass correlation tables. This was plugged into H outer, and calculated to be 429.5 watts per meter squared Kelvin. After plugging in both H inner and H outer, as well as our radiuses, into the conduction equation, analytical and numerical, it was found that the temperatures were fairly close, as the conduction equation for the analytical at our temperature at our inner was 46.67 and at our outer was 36.42, while in numerical the temperature was 49.9 at our inner and 37.05 at our outer. Solving for the heat transfer rate, it can be seen that the heat transfer rates are relatively low, as we are getting 0.013 and negative 0.0296 for the numerical, and only negative 4.9 kilowatts and negative 0.148 kilowatts for the analytical. The numerical is more accurate than the analytical, and it can be seen that the heat transfer rate is very low, so our insulation is working as it should be and is preventing heat loss. Also, the fact that the temperatures were relatively close to our initial guesses prove and are close to each other prove that these calculations are accurate. Thank you.